going to continue. We're going to work a lot of problems today in 14s. Then we'll do our pre-lab, but we'll spend a good while. A lot of problems are like some of the things that you're going to need to do in the Mastering Chemistry. So if you haven't done those, maybe you can get some tips with what we're doing. First one's problem number 36. So I've got a graph that's a plot of the reaction rate versus the concentration of the reactant. And a couple of things that wants me to take this piece of information and make some decisions about it. The first thing it asks is, what is the order of the reaction with respect to A? And it doesn't tell me what the reaction is. Only thing it tells me is that this reactant A is being plotted and how the rate's changing with respect to that. And what we see in the graph is it doesn't change at all. Okay, it's absolutely constant. So if we think about the types of reactions, I think I've got those on the next page. We talked about 0, first, and second order. There was only one of those where the rate is not changing as a function of the concentration. So which one would it be? It'd be a 0 order. So the fact that the concentration goes through this range from 0 to 1 and the rate remains the same means that this reaction is 0 order. So the rate equals the rate constant K times the concentration to the 0 power. So anything at 0 power is just 1. So the rate is just equal to the rate constant K. All right, so if it's B says make a rough sketch of what would happen if A versus time. So if we look at the concentration of A versus time, and you could start at any concentration, the result's going to be the same. If it were 1 molar as your initial concentration, the fact that the rate's the same and it's consuming the reactant at exactly the same rate, that's just plot's going to be a straight line, okay, falling off with a negative slope. Constantly consuming it at the same amount, because regardless of which concentration you have through here, it's always exactly the same. All right, C says write the rate law, including the reaction for K. So that one's where we're going to have to look at the graph and give us some information. So this is the rate law expression that we have. So the rate, we said, since it was A to the 0 power, is just equal to K, but we don't have the value to K, for K given to us. But we can look at the graph and see that the rate on the graph is going to be our value for K. So it's just reading the value from the graph. 0.011 molar per second. All right. So question on that one. Okay. All right. So gathering information about a graph. So our next one is we have this reaction. It's dinitrogen tetraoxide, or pentaoxide, so N2O5, and it decomposes to NO3 and NO2. So it says the rate constant at a certain temperature is given. So we know what K is in this system. So that's what K is. It says calculate the rate of the reaction when the concentration of the reactant is 0.055. And then B, it wants to know what's the rate of the reaction would be indicated if it were second order and then 0 order. Well, let's just start with A first. So the rate is going to equal to K times the concentration of the N2O5 and then raised to the power of the order. Now, it's kind of where we got to read the things in the problem and recognize what it tells us. In the wording, it tells us that it's first order. So I know what that number is. All right, so I don't have to solve it. So all I have to do is plug K in. And it has units of inverse seconds times the initial concentration. And the initial concentration is the 0.055 molar. And multiply those two things together. And when I do, I'll have the rate of the reaction. And 2.92 times 10 to the minus third. And rate is going to be molar per second. and I've got molar over seconds, so that's what I expect to find. All right, so that's A. Let's go ahead and at least answer one of the other ones. So let's do what it would say in B. So B, it wants you to do different orders. So it wants to know what the rate reaction would be if it were zero order. So if it were zero order, it just changes so that this becomes zero. So that term drops out. So the rate's just going to equal to K. So 0.035 molar per second. And then if it were second order, you would just plug it in to the second power on this term. If it wanted to know second order, the same way we did. Okay, so we just plug in the value with K that's given, the initial concentration raised to the power of the order, and it's just wanting us to look at the other values for orders. But in rates are always need to come out in units of molarity per second. The rate constants are what change. Okay. And that's one thing that doesn't make sense on the units in this problem is that this units of K being inverse seconds, that's only good for the first order. So go back to our table that we have. So if we look at how K varies, for it to be a zero order, it needed to be molarity per second. For first order, it's inverse seconds. For second order, it's inverse molarity, inverse seconds. It needs to change with every one of these different things that's in the problem, and it doesn't give us that piece of information to answer that. All right, problem 40 says you've got a reaction that's got A, B, and C react to form products. It's zero order with respect to A, it's half order with respect to B, and second order with respect to C. So just for the practice of writing these, we're going to look at some things that are non-zero first or second, but I'm not going to test you over it, but we can work this problem. We still need to see the other parts of it. All right, so the first thing it says is write the rate law. So the rate law is going to equal to K times the concentration of the first reactant, and that's A, and then raised to the power, and it says it's zero order with respect to A, and then times the concentration of the second reactant raised to its power. It's half order with respect to B. This is the one that I won't give you. And then with C, with respect to C, it's second order with respect to C. So basically that middle term, or the first term, this becomes a 1 and it just drops out of it. Okay, so it wants to know what is the overall order of the reaction. So let's just work on answering some of these things. So on B, what is the overall order of the reaction? Well, we sum together all of the different terms. So it would be 0 plus 1/2 plus 2. So it'd be 2 1/2 order overall. All right. C says, and this the parts below are the ones that I want us to play with a little bit. So let's look at let's see. So C says that by what factor does the reaction rate change if the concentration of A doubles? So if I think about the reaction, what I'm wanting to look at is how is the rate changing if the concentration of A is doubled. So if A is to the zero power, if I'm taking and I want to compare that rate 1, okay, versus a rate 2, where rate 2 it's going to be 2 times the concentration, so it would be 2 times the concentration of A naught, whatever that original concentration was, but it's still the zero power. It doesn't matter what it is, this is still going to be 1 in both cases, so they would be the same. So the rate is the same regardless of whatever the initial concentration is. So it doesn't change on that one. All right, so B says, by what factor does the reaction rate change if B is doubled? So let's look at what happens with B. All right, so So now we go down and we do our comparison of the rate. So rate 1 is equal to K times, and we look at what's happening with B. And B is to the 1/2 power, so to the 1/2. And then we want to compare that versus rate 2. And rate 2, it's still going to be the same thing, but now it's going to be 2 times whatever B was, raised to the 1/2 power. Okay, so if we look at this one, we basically just need to factor the 2 out and get it onto the other side so we can do a comparison of rate 1 and rate 2. So if I take this 2 out of it, I've got to take the square root with it. So to get rid of that, it would be 2 square root. So the comparison is when you do 2 square root, that means the rate would be 1.4 times faster. Than rate 1. All right, so why 1.4 times? Because the square root of 2 is 1.44, whatever it is, rounds out. So it's going to be 1.4 times as fast. All right, so let's look at comparison for E. So E says, what factor would it change if C is doubled? All right, so on C, compare rate 1. So it'd be the concentration of C. And now it's squared comparing to rate 2. The K times 2C and square it. So to get them the same, I need to factor this 2 out to the other side. So take the 2 out, but the square has to come with it. So 2 squared is 4. So rate 2 would equal to 4 times rate 1. So 4 times faster. Somewhere in that, I'm going to give you an expression, tell you the order, and on the exam, I'm going to ask you, if I double, triple, change this concentration by factor, how's the rate respond? So you need to be able to understand how to take a rate law and then look if I change any of the concentrations, how's the rate overall respond? You got some mastering chemistry problems just like that. Question on this one? Easy enough? Okay, maybe. Right, 42 says, consider the initial rate. A decomposes to products at several different concentrations. What's the order of the reaction? Write the rate law, and then find the value of K. All right, so first thing it wants to do is determine the order with it. So we know some initial concentrations, and we know what the rate is. So what we need to do is do a comparison to see how the rate is changing as a function of concentration. Now we've got 3 different trials here, and they're all the same reactant. We could use any comparisons. We could go from if I number these, go from 1, 2, and 3. I could compare 1 to 2. So 1 to 2, the concentration doubles, and if I look at the rate, it goes from 0.008 to 0.016. It's twice as fast. So 2 times the concentration, 2 times the rate. What does that tell me the order is? It tells me it's first order. Now what I want you to understand is it didn't matter which concentrations I chose. So would it matter if I used 1 and 3? If I chose 1 and 3, it would be 4 times the concentration. But if I looked at the rate, it was 4 times the rate. Still 4 and 4, still first order. So it didn't matter which pair you picked. You just choose 2 different concentrations to compare. Okay. Right. It's easier if they're whole numbers. So twice as much, 4 times as much versus something that's not. So if it was in here a fractional amount, well, that wouldn't work. Let's make it 150. So it would be 3 point something times. Still, if you knew however many times it was, you still could figure it out. It's just easier to see if it's integer values. All right, so we know it's first order. So the next thing says write the rate law, writing the rate constant. So we need to know what the rate is. And we know what the order is at this point. We know what A is, and it's first order to that power, but what we need to know is include K in this. So we did problems like this, and on the clickers, we need to find out what K is. Once we know it's first order, we know that K is equal to the rate divided by the concentration to the particular order, which is 1 in this case. I can take any of the trials. I'm just going to choose the first one. And the rate is 0.008 molar per second. And the concentration is 0.15 molar. So oops, let's get over here. The molarity is going to cancel out. And I get a rate value of 0.0533 inverse second. So now simply to write the complete rate law, including the value of K, I would just substitute that value in the system. Inverse seconds times the concentration of A. Okay. So to answer the question as it asked, write the complete one. That would be this term at the bottom. Question? Why is the units for the rate? Why is it different? Okay, the units for K. Oh, sorry. Yeah, so this is for K though. So that's the reason it's different. And remember, for every what we talked about on the previous one, the K's are different for every one of them. The fact that we figured out that this is a, go back now, one more slide. The fact that we figured out it's a first order, units of K are inverse seconds. So if it were a 0 order or a second order, it would have been different for each one, all three of those. Okay. All right, so 45. This one's slightly more complicated in the fact it's a similar problem, but it's got two values or two reactants. So we want to try to look at conditions where we can solve the order with respect to each of them. I'm going to number them so we did 4 trials. Okay, so I'm looking at ones for the first reactant, the NO2, where the concentration of the F2 is the same. So the F2 is the same on this one, and on this variable it doubles. And if I look at the rate, what happens with the rate increased almost by a factor of 2, so it's twice as much. So what that means is that if I think about the rate expression, rate is equal to K times the concentration of the first reactant times the concentration of the second reactant. And I'm trying to find out what these orders are. With respect to the NO2, it's first order. Now this is a good example where regardless of what the stoichiometry is, we have to determine it experimentally. Okay, so you can't look at that 2 out in front and assume it's second order. All right, so now we look at the second set of conditions and try to figure out what the order is with the other reactant. So I want ones where the NO2 is the same. So the ones where the NO2 is the same are 2 and 3, and on this one, the concentrations of the F2 is doubled. The concentration of the F2 is doubled, and comparing the rates of it, the rates almost double. So that tells me this one also is a first order. Okay, so now I know that both of them are first order. It wants me to calculate the rate constant K. So I'm looking for what is K in this system. So K is going to be equal to the rate divided by the concentration of the NO2 and the concentration of the F2, and both of those to the first power. So I could pick any of the trials. I'm just choosing the top one, 0.062 molarity per second divided by the concentration of the NO2, which is 0.1 molar, and the concentration of the F2, which is also 0.1 molar. So I'm dividing by 0.1 twice. So 2.6, right? Yeah. All right, 2.6 is the numerical value for K. And if I look at the units of molarity, its molarity on bottom cancels out with one of the molarities on top, but I've still got a molarity on the bottom, so the units for K are inverse molarity, inverse seconds, and that's what I expect for something that's second order overall. Okay, because it's first order plus first order, and that's what the last question is what is the overall. So if I wanted to write the overall rate expression with a K, it would be rate equals to the rate constant, 2.6 inverse molar inverse seconds times the concentration of the NO2 times the concentration of the F2. And both of those are the first power. And if the first power is this concentration. Question on that? Easy enough? Okay. All right, so let's look at another one. What did we do here? Ain't that quick. Okay. Better go clear the. Thought I had saved those. Clear it out. That's the one that we just did. Okay, so let's look at our next one. So we got our rate law table in here. So the problem 48 says indicate the order of the reaction that's consistent with the observation. And then something I did was I copied this portion of the table. So this far right-hand side, this is the table that you're going to get for the test. This table 14.2 book, it's the summation of all the stuff with the integrated rate laws. So it gives you the rate expressions, the units expect for K, and the integrated rate laws, what you would plot, and it gives you the half-life expression. So I just copied those half-life expressions because that's what applies to the part A of the problem. Okay, so the first one says the half-life for reaction gets shorter as the initial concentration is increased. So you have a decreased half-life, so T half is half-life. That goes down when the concentration of the reactant increases. So if we look at the different equations that we have to express the relationship between the half-life and the concentration of the reactant, if we try to figure out which one this is, we're looking for the one that as A gets bigger, it's going to make T smaller. So if this is 0, this is first, this is second order. So with the 0 order, as the concentration goes up, the half-life concentration or time would go up because the time half-life would be proportional to the concentration initially. So it's not a 0 order. All right. If I look at first order is not dependent on time at all, or concentration at all. So it's not a first order. But if I look at the second order one, what happens is this number gets bigger for the concentration, since it's inversely proportional to the time. As this gets bigger, that makes this smaller. That's the case we have on this one. So that means that this one is a second order reaction with respect to that reaction. All right. B says a plot of the natural log of the concentration versus time. Okay, that yields a straight line. So this is where we can go back to our reference in the table. On a zero order, a straight line is concentration versus time, so it's not a zero. On a first order, the natural log of the concentration versus time is a straight line. That's the one we have. So knowing that, that tells me this one is a first order. Okay. On C, it says that the half-life gets longer as the initial concentration is increased. So we know that's not the second order because we've already used that one. If we look at is it first order? First order, it doesn't matter what the concentration is, the half-life stays the same, so it's still not a first. But on the zero order, as the concentration goes up, since it's directly proportional, the half-life time would go up. So that means that that one has to be a zero order. Okay. So something like that's going to be a test question. Okay, problem number 50. So we've got some data for the decomposition of N2O5. It decomposes to NO3 and NO2. We've got from 0 to 200 seconds and 25-second intervals. And I need to know what is the order of the reaction. And then I also want to know the value of K. So the order, what is the order of the reaction? And then I'd like to know the value of K. So the way that we determine the order for the reaction when we've got time data is we need to graph it. Okay, so we have to look at it graphically to answer this. So I went in and take those values and put them into Excel. Maybe I did. All right, so that is problem 50. Yeah. Save. Okay, so if I plot just concentration versus time, and if I look at that, so I'm going to go insert a graph, and I see that this concentration versus time is not a straight line. Okay, so it's not a zero order because it would be a straight line if it's zero order. So what we're doing is we're looking back and seeing we've got to make all these plots to try to figure out what the order would be. So if it were concentration versus time and it were zero order, it'd be a straight line. It's not that one. Okay, so we've got to go back and do the next one. Let's see if it's first order. We want natural log of concentration versus time. So let's do that plot. So cancel that out. All right, so I'm going to make a new cell that's called natural log of concentration. And so it's equal to ln, open parentheses, the value in that cell, close parentheses, and I'm going to drag it down. Okay, so now I want to plot that versus time. And copy the time data over. Simpler. And I'm going to go make a plot of that. So insert the graph. Right, so that one looks fairly straight. Close up so you don't see it easier. And then if it is straight there, which I think it is, I can verify it's straight by drawing a line through it. So I'm going to right click on the data. I'm going to tell it add a trend line. And it says what kind of trend line you want. The default's linear. That's what we're trying to get. The key thing is I want to see this equation. So the equation, here's my equation that y equals mx plus b. So now I've got an equation that tells me something about it. I know the mathematical relationship. If I go back to the table, it tells me that looking at the slope, that the slope is equal to a negative of k for this. So I need to look at the slope. The slope is a negative 127.69. So now I know that piece of information. I know that it's a first order, and I know the value of the slope. So negative, I've got a terrible memory with numbers, so I'm writing it down, 127.69. And we'll we'll go back and look at we know that portion of it. So we know, what do we know? We know that the order is first. All right, so now we need to know the value for the rate constant, and for the rate constant, it told us that the slope is the negative of k. So the answer of what k is just equal to a negative of the negative 127.69. So that's going to be just a positive 120, probably round it to 128. All right, so if we look at what would be the units of k, what are the units of k for our first order? Inverse seconds. Okay. Now, what it wants to do, now I know that piece of information, I could write the expression out, but it wants to know what is the concentration of the time of the reactant at 250 seconds. So it wants us to take that information that we're given and predict what would the concentration be down here at 250 seconds. So whenever we want to solve what concentration is as a function of time, the equation we use is the integrated rate law. All right, so what we're going to use is the integrated rate law. That's what the IRL stands for. So let's go back and look at the equation we have for the integrated rate law for a first order. So we've determined it's first order. This becomes our equation that we're going to look at. The natural log of the concentration of a function of time is equal to negative KT plus the natural log of the initial concentration. So the natural log of the reactant concentration at 250 seconds is equal to a negative KT. So it's a negative of 128 inverse seconds times the time, and the time is 250 seconds, plus the natural log of whatever the original concentration was, or initial. In this case, it's 0. All right? So the natural log of 1 is 0. So this term falls out. I take my 128 times 250, and I get a big number, 32,000. Okay, so 32,000, and got to remember the negative in front of it, so it's a negative 32,000 equals the natural log of the concentration of the N2O5. So if I want to find out what the concentration of the N2O5 is, I've got to take the anti-log of both sides. And that bombs my calculator. So, all right. What if I got negative KT plus the natural log of A. Initial concentration, negative KT, 250 seconds, 0, negative KT. Okay, I want to go back to my graph then, make sure I got K right on my graph. So I'm plotting. Okay, I see what I did wrong. So what's supposed to be on the plotted on the x-axis is I'm supposed to have plotted time on the x-axis, and I've got the natural log on the x-axis. I've got them swapped. So I need to take, and I can just simply right-click on the data. I think I can tell it to swap the x and y. Let me do it this way. replotted. Do the same thing, add a trend line, display the equation. All right, now that number maybe makes more sense. So 0078. At least it's going to make sense with this calculation. Zero zero 7 8 seconds. All right. It's plotted right at L. All right, so now we can throw our numbers back in. Going to change that. All right, so negative 0.0078 times 250. So that's a negative 195. That's a lot more sense. I take the negative analog of that. Get 0.4 or 142 molar. That's the concentration of N2O5 at 250 seconds. Now let's see if that makes sense. At here it was 0.12 or 0.21, so it makes sense for it to be at that value 50 seconds later. It's getting smaller. Question on that one?
On the test, I guess we're going to have a question like this. Are you just going to give us a graph of that slope or anything?
Yeah, if you look at the old tests, obviously you can't plot them in Excel. So sometimes I'll give you a graph. Sometimes I give you all three graphs. So I don't just give you the graph of the one you utilize. I'll plot all three pieces of information out and put them there. You have to choose the one you use. But you're just looking for the one that's linear. But I want you to recognize you've got to know which one to use and not just, you got to figure that out. Yes?
On K,
On the what now?
okay, would it change?
This K, yes. So this K was this value.
Okay.
0.0078 negative. Okay. Other questions? You have a master in chemistry. Somebody emailed me about this exact question, or not this exact one, but one just like it. You got to take and plot the data out, and you got to figure out from one of the master, or I don't remember the problem number, but you got to plot it out to figure out what the order is. Once you do the order, you got to find the slope of it. From the slope, calculate what the rate constant K is. Okay. All right, so let's look at the next one, guys. So 54 says a reaction is monitored as a function of time. It's AB decomposes to A plus B. A plot of 1 over A versus time yields a straight line, and it gives you the slope. Then it wants to know what's the value of the rate constant at this temperature. B, what's the rate law for the reaction. C, what's the half-life given an initial concentration. And D, if the initial concentration is 1/4 molar, what's the what are the concentrations of A and B after 75 seconds? So let's all of those are good examples. So if we look at it, a plot of 1 over the concentration of the reactant versus time is a straight line, and go back to our figure out which one that is. The one we plot 1 over concentration versus time is a straight line. That means that it's a second order reaction. Okay, so we know it's a second order, right? So now we look at how the relationship is for the slope for second order. The slope is equal to K. All right, so we can answer a few of these things just by that. So we want to know what the value of K is. K is just equal to the slope M, and that's provided in this one. So it's the 0.55 inverse molar inverse seconds. And we know that piece of information. All right, so now it wants us to write the rate law for it. So in B, I want to write the rate law. So the rate is equal to the rate constant times the concentration of the reactant. There's only one, raised to the order, and this one's second order, so 2. Okay, so now we've got the expression. All right, so C is the half-life question. So let's look at what would happen with the half-life. So on C, we know it's second order. The relationship for half-life is the half-life is equal to the inverse of K times the inverse of the initial concentration. So the half-life is the inverse of K times the inverse of the initial concentration. Right? And it tells us that we know what K is. It's 0.55 inverse molar seconds. So that means it was on the bottom, now it goes to the top, and then times the concentration, which is, or 1 over the concentration, which is 0.55 molar. They're both 0.55. That's a little weird. But I'm left with seconds on top for time. So the 55 3.3 seconds. So if you started with 1 molar in 3.3 seconds, you'd have half a molar. Okay. Problem D. So problem D is, what is the concentration as a function of time? So it's 75 seconds. So I want to know what is the concentration of AB at 75 seconds. That's what I want to know. All right, so this is an application of the integrated rate law. So we've got to go back and look at the equation for the integrated rate law for second order. So for a second order, it's 1 over the concentration is equal to KT plus the inverse of the initial concentration. All right, so we just plug things in and crank that out. So 1 over the concentration of AB at 75 seconds is equal to, let me say it, KT. So K was 0.55 inverse molarity seconds, and then times T, which is 75 seconds, and then plus the inverse of the initial concentration. And the initial concentration on this one, it tells us, is at 1/4 molar. So what we're solving for when we multiply this out is not what the concentration of AB is, it's the inverse of AB. Okay, so we just do the math and find out what's on the right. So on the right, I get 45.25, right? And the seconds cancel out. I've got inverse molar and inverse molar, so the units are inverse molar. So that is equal to 1 over the concentration of AB. So if I want to find out what the concentration is, I take the inverse of both sides, so the -1. So the concentration of AB at 75 seconds, just the inverse of that, which is 0.022 molar. So it's decomposed to a fraction of what it was, and that makes sense because every 3.3 seconds it's going through a half-life of it. It's disappearing really quick. So at 75 seconds, I've used a bunch of half-lives. So on my calculator, once I got this value, my calculator, I got this button called the 1 over x button, or x to the minus 1.
So did you do the 0.55 times 75 divided by 0.25?
No, I just took, to come up with this number, I just took, did this in parentheses, did this in parentheses, and then added them together. So multiply those together, close our plus, and then open set of parentheses, invert that, and then add them together. And that should come up to the 45.2. Okay. All right, so next question is talking about radioactive decay. So 58 is talking about the C14. So we use this in radiocarbon dating. You've heard of this. So radiocarbon dating looks at the ratio of the different isotopes, carbon. So those are the C13 or the C12, the most common, the C13 and the C14. Both C12 and C13 are non-radioactive. They're stable isotopes. So however much carbon's there, again, back in a million years, there's still that much carbon there. But the C14 is radioactive. It decomposes. That doesn't decompose quick. The half-life of it, so this is the half-life of it, is 5,700 years. So it's not happening quick. But the ratios of these, if we look at the most abundant is the carbon. It's that's going the wrong way. So this would be, we'll say 1 to 100th to about 1/100,000th. So by far, you've got 99 of these for every one of these guys, and then just very, very rarely you have one of these C14s. Okay, so it tells us that the half-life is independent of concentration. Now, there's only one of the types of reactions where the half-life is independent of concentration. Which one is that? So I'm going to go back to our page. The one that doesn't depend on concentration, zero order does depend on concentration. First order depends on concentration. The fact that it tells us that tells us that it's got to be a first order. So it's not a second order, it's not a zero order, it's got to be a first order. So the equation is that the half-life is equal to the inverse of K times 0.69 or 0.693 divided by K. All right, so the half-life is equal to 0.693 divided by K for first order. All right, so the things that it asks us with this is how long does it take for 70 or 25% of the C14 atoms to decay. So if we think of what's going on with that, to go from 50% or from 100% to 50%, that's the definition of what a half-life is. So that takes a half-life. To lose half of that, half of the original 50 would take it to 25%. That would also take another half-life. So that's an easy one to answer. You just add together the time for the half-life is the same. It's 5730. So that would be adding that together 1460. Is that right? Whatever that is, add it together twice. Okay. All right. So the last part of the question is the trickier one. All right. So the last part of the question says a sample originally contains a certain amount, a number of millimoles of C14. how many millimoles are left after 2,255 years. And this is what we do when we do carbon dating. So when we do carbon dating, as the CO2 that's in the air, or the carbon that's in the air in the form of CO2, goes up to the upper atmosphere, it interacts with the radioactive gamma rays coming from the sun. And that makes this ratio of C14 to C13, the closest, more abundant one, at a fixed ratio. But as soon as this C14 gets fixated in something where it can't go into the atmosphere anymore, whether it gets into a fossil or to a piece of wood buried in the ground or whatever it is, so it's not exchanging in the atmosphere, now this ratio starts to drop because that C14 is starting to decompose. And we know that if half of it's gone, if this ratio doubles from what it was, it's been 57:30. And we can do a comparison. That's how we radiocarbon date, is we look at the ratio of these two isotopes. We measure that ratio with a mass spectrometer, and we look at exactly what that ratio is, and that's how we radiocarbon date. Okay, so, but to answer this one, it tells us an initial amount, right? So if we think of, do we have to do this in concentration? No, we can do it in moles as well. The other thing that's a little different on it is we usually talk about half-life in seconds. This one is not seconds, the half-life is in years. That's fine, it's a unit of time. It'll work the same regardless for it. But to be able to know what it is as a function of time, I've got to apply the integrated rate law. All right, to answer the integrated rate law, I'm going to go back to our formula. So we said that this one is a first order. To be able to solve this equation, I've got to know what K is. All right, so how can I solve out what K is in the system? Because I know that this is 5730 years, right? I can take and rearrange this for K, so that means that K is equal to, so I'm solving for K, and I'm going to just swap these. So K is equal to the 0.693 divided by the 5730 years. It'll be a small number because it's a very slow decay. Put it in scientific notation. And the units we have for it, normally it's inverse seconds. Here it's inverse years in this case. Okay, so now I know what K is. I can go to the integrated rate law. So the integrated rate law for first order says the natural log is a function of time is equal to negative KT plus the natural log of the initial concentration. So I'm going to plug that into the problem. I've got to find my change of color. All right, so the natural log of the amount or concentration at 2255 years is equal to, remember our formula was a negative KT. All right, so it's a negative of the rate constant times the number of years, 2255. I'm going to cancel that out for units. All right, and then plus the natural log of the initial concentration or amount, which is 1.55 or 1.5 millimoles. Okay, so I take and multiply these. I take the natural log of this and add it together. And I get 1.328 times 10 to the minus 1. Okay, so that equals the natural log of A. Find out what A is. I take the E of both sides. So that's going to say that the concentration of C14, or the amount of C14 that's left after 2255 years, 1.142 millimoles. Okay, does that make sense? Well, kind of does. I had 1.5 to start with. I'm down to 1.1 of it. I haven't went through a half-life yet, or even half of a half-life, so most of the sample's still there. So it's that principle how we would use to solve this equation backwards to find out how long something's been out in the environment. Now, when we do that plot, when we plot the ratio of C14 to C13, right? So it starts off big and it's highly measurable, and as the C14 disappears, it gets harder and harder to measure. So how far can we go back to and measure accurately? Going back to about 50,000 years, we can do it pretty accurately. So within the last 50,000 years, we can measure something literally within 10 years with a pretty good degree of precision. Going back further than that, it's a little tougher to do because the amount of the carbon C14 that's there is so small it's hard to measure. Now, in the last few years, we've had some good advances in the technology of the instruments that make these measurements, and our accuracy that we can make these numbers, we're now back to about 250,000 years. So we can go back even further, and that's pretty recent technology. This is a pretty, in terms of science versus religion, this is a hot button topic. So there are a lot of faiths that say that the Earth is 5,700 years old, and therefore nothing is this old. So your scientific data is flawed. So I've had several heated discussions with pastors that were very passionate about their faith. Had these type of discussions. I've had students that have chose to write, "This is not possible" on a test and turn it in, and I respect your view, but mathematically you still need to give me the scientific answer for what it is. So that's your choice to have that review, and I respect that. That's your faith points you in that direction. But this is just kind of one of the hot buttons that where you have a discrepancy of what science indicates today and what people's faith teaches them. And these types of the disagreement between what religion is and what science shows, those are things that have been going on throughout society. Going back to the first major case that became public was Galileo Galilei. They were going to burn him at the stake because of the invention of the telescope and him showing data showing the world that the Earth doesn't, everything doesn't revolve around the Earth. They looked at the telescope, they could see things revolving around Jupiter, the moons of Jupiter, and they considered that anarchy. They considered that to be a complete insult to the faith, and the church in Spain actually, at the Inquisition, recommended that they burn Galileo at the stake, but he still got life imprisonment out of it. They locked him up because of having a view that differed with that of the church. Okay, so 64. And I'll tell you, this problem, that's a tough one because that's a critical thinking at the highest end. You have to figure out first, is it a first order reaction by the key wording that's independent? Then to do the one at the bottom, you've got to solve the integrated rate law. To do that, you have to know what K is. So once you know it's first order, you'd have to solve for K, then plug it in the integrated rate law. That's all the pieces put together. It's a tougher one. So is it impossible that you would see a question like that? No. Would it take a lot of time to do it? Yes. If you look at the old test, I give you questions that would be much like this one frequently, all right? But I don't know that I've ever asked one like on the bottom. Does the final exam? Yes. The final exam is going to have a few questions on it that are significantly harder than other ones. That's one of the types of questions they'll talk about. And in the last chapter, we'll do chapter 20. We're going to talk about radioactivity, and we'll review things like this, how the kinetics of radioactivity come into play. All right, 64 says the rate constant for a reaction is measured as a function of temperature. A plot of the natural log of K versus the inverse of the temperature has a slope, and what is the activation energy for this reaction? Okay, so down here at the bottom, we've got our equation. This is the Arrhenius equation. It's the natural log of K versus 1 over temperature, and it tells us the slope of this reaction that's plotted. So natural log of K versus 1 over the temperature in Kelvin. And it's got some line, and the slope with it is a negative 0.101 times 10 to the 4th K. So we want to know what is the activation energy. So the key thing, if we look at this term, we know that the slope, because if this is y equals mx plus b, we know that this is the x-axis, then this is the m. So the slope is equal to the activation energy divided by r, and it's actually a negative of that. Somehow I didn't get a negative stuck in front of that guy. All right, so if we want to know what the activation energy is, we need to multiply both sides by negative r. So the negative would cancel out. Negative, negative make a positive. The r's cancel out. So the activation energy is just equal to the slope, which is 1.01 times 10 to the 4th, times a negative 8.314, the value for R. And we're going to get the answer in joules per mole. And it's 8.40 times 10 to the 4th joules per mole, or 84 kilojoules per mole. We put in kilojoules per mole. Yes?
Is there a difference for the negative EA?
It's always positive.
Okay, so why is it negative EA?
Okay, the slope, this should have a negative in this. I wrote it down wrong. So there should be a negative right here in this. So when you set this up, this relationship is always negative E sub A.
Didn't we do some yesterday where the E sub A?
That's the 2 point, and we're going to get there. So this is the 1 point where you're plotting the natural log of K versus temperature with the 2 point equation, which is, I'll show you on the next page.
Yeah, because that's K.
Yeah, yeah. So on this guy that we did, that's the difference there. I understand exactly what you're asking. Okay. All right. Problem number 7.
Yeah, let's get.
Okay, and we had the same issue or thing with the Clausius-Clapeyron equation. So the same thing happened with it. That's the reason there's a lot of similarities between those two equations. Okay, but when you do the 2 point equation, the negative disappears. All right. So problem number 70 says the rate of a reaction is a certain value at 27 degrees. It's another value at 77 degrees. Determine the activation barrier for this reaction. So this means the activation energy. Okay, activation barrier and activation energy mean the same thing. And then the second thing, once you know that, it would want to know what is the value of the rate constant at 17 degrees. So let's choose both things to do both of them. Well, the first thing I've got to do is get the temperature into Kelvin. Okay, so I'm going to take those numbers and add 273 to both of them. So the first one's easy. So 300 Kelvin. 350 Kelvin. All right? And then I've got to choose to pair them up, right? It doesn't matter which ones I call which. I'm going to call this one K1 T1, K2 T2. So now I know what the values of K1 and 2 are, T1 and T2 are. I know the value of R is 8.314. The only thing I need to do is solve that question for the E sub A. Okay. So let's just crank through it. All right, so K2, and I said K2 is 0.228 divided by K1. The zeros in there. Okay, equals E sub A. R is 8.314 joules per mole 3 Kelvin times the inverse of T1. So 1 over 300 less 1 over 350. Okay. So only thing left in that is E sub A. It's just cranking through the math to get the answer to that. So the approach that I would use is to find what's on the left first. So I would take this ratio. So 3 zeros, 1, 2. Then I've got the ratio inside the parentheses is 1869. Take the natural log of it. So on the left-hand side, I have 7.533. I would take and multiply this R to this side. So 8.314 joules per mole. The Kelvin's going to cancel out with the inverse Kelvin on this one. So those would cancel out. Right, so that gets rid of this term. So I need to find out what this one is. So it's going to be equal to E sub A. So 300 inverse. That's 350 inverse. And inside the parentheses, this is 0.000476. So that's on the top on this side. It's going to go to the bottom on this side. So divided by 0.000476. All right, so divided by 7.533 equals inverse. Oh, somebody else got this number? $131,000.
136.
I put a number in wrong. Oops. I got close to it again. I'm off a couple of digits here, but I got 131.5 again. So in kilojoules, 131.5 kilojoules per mole. Okay. So that answers A, what is the activation energy? So to do part B of it, it wants to know what's the value of the rate constant at a certain temperature. So to set this one up, we know what E sub A is. We're looking for what is a rate constant at a temperature that's given. So we would solve it for K2. All right, so let's just set that one up. So 17 degrees is 290 Kelvin. So the natural log of K2, and it wouldn't matter which one of the other ones we use. We could use this pair, or we could use this pair for the other one. Okay, I'm just going to choose the one with the bigger numbers because I don't want to write all the small numbers. So K1 is 0.228. So I'm calling this one set now K1 T1. This is going to be our one we're solving for. So our T2 that we're going to have for this one is our 290. right? So on this side of the equation, we've got, we need to put it back into our joules per mole, R 8.314. And we've got our inverse of our temperatures. So T1 is our 350. So T2 that we're solving for is the 290. Everything on the right-hand side is just a number. So parentheses 350 versus 20 equals. All right, I get that the number on the right-hand side is negative 9.350. Anybody else get that? Double check my math. I got the same thing again. So if I want to get rid of the log, I take the anti-log of both sides. .7 times 10 to the minus fifth. Okay, so that equals to, when I take the anti-log of the log, that's going to be equal to K2 divided by 0.22228. Yep. So that means if I want to know what K2 is, I've got to multiply this to this side. So times 0.228. K2 is 1.98 around the 2 times 10 to the minus fifth.
So it'd be the e to the negative 9.35 times.
Well, that's what I did. So
Yeah, e to the negative 9.
right. So this value is this value. So where I'm multiplying this number times that. Okay. So question like that, either way, you're going to have one of the two. You're either going to have solve for an activation energy, or given the activation energy in one set of temperature and rate, solve for the other temperature or rate. Okay, so that's something that's coming. And again, if you can just get to the point where you set it up, you get half the questions. All right, so 72 is a very similar question. I'm not going to work that one because we need to do our demo. I want to show you something I'm playing with, though. So there was an article published about pheromones. So pheromones are a class of compounds that mammals, insects, everything emit, and they're very close to their class of the hormone family. So they're things that are volatile, they go airborne, and they tell all types of information. It's when ants, things that you've observed in nature, when ants walk, ants always walk the same trail. So even though one ant is hundreds of yards from where his ant pile is, another ant can follow him exactly where he went to come get food. All right, so it detects those pheromones. Same thing with butterflies. There's some more common pheromones that we've heard that are called that people are attracted to each other. So there's attraction that's chemical systems that we have. So we think we have a good understanding about some of these, but there's a thing that came out with new. There's a pheromone that's been released that relates to the nitrogen on the tree. So that's pretty cool. concept that now that they've got the ability to look at that. So what I've been working with some of the other chemists in the state, and we've been trying to come up with a way that would detect that particular pheromone. And if it works, we've got a pretty cool system. So now we can detect somebody. So it would be equivalently a chemical lie detector test. All right, so here. Okay, so putting a couple of reagents in here. The reaction doesn't start until I put the last reagent in, or it doesn't have the ability to sense. So I'm going to squirt it in here, and I'm going to mix it up good. All right, so what it's looking for, the reactivity is this volatile compound that's going to come out of the air. So it's going to come out of somebody's skin. Things we know, once it emits off the skin, it travels through air really quick as a gas phase, and then it would be absorbed by the reaction, and the reaction would be triggered by changing colors. Anybody want to be a volunteer? Okay, come here. All right. All right. So stand where I am over here, and put your hand over the top of this. So leave it a couple inches over the top. All right. So what we got to do is we got to ask you a question, and then we got to wait just a few seconds to see is it going to change or not. All right. So
Wait, silicon line?
that's if it works, that's what it should do. It should emit the pheromone.
Okay.
All right. So are you a student in Southeastern?
Yeah.
Okay. So let's wait a few seconds. Anything that happens.
Should I lie on that one? I don't know.
Well, we're gonna see.
Don't make it obvious stuff.
Okay. All right. So, all right. Did you cheat on the last exam?
No, I did not. I didn't.
Didn't. Okay. So this is a time reaction, and my wife falls for this every time. So it's a fun trick to play on people. But this is the kinetics reaction that we're doing in today's lab. So I know I was watching the clock. It took around 130 seconds to change. So, not
Terrible.
fast.
That was not funny.
Okay, so you get your stopwatch out on your phone, and let's measure it precisely this time. So I'm putting 1 ml of each of these reagents in. All right, and go. Okay, so I expect nothing to happen for the first minute and 28 seconds, but plus or minus about 5 seconds at a minute 32 or 33, I expect a color change.